Okay, I'm Dan. Um, I'm doing the risk analysis. Some of the major concerns that we have in this project is the power management. Since each motor that we're using can draw upwards of 8 amps, we have to have safe wiring and encasement of these circuits and wires. Mainly because since it's going to be in a kitchen, there's going to be water, and if that gets in the system, then it could potentially short out one of the circuits and provide some danger to Doug or like anybody that's using the robot. So for operating speed, our sponsor specified that he wanted the robot to move at variable speeds. But to do this, we want to keep it within a certain range where it would not, a certain speed range where it would not like hurt someone if it ran into them, or since it's carrying pots of water, if it goes too fast, then potentially it could spill boiling water on the person using the robotic arm. So to do this, we're gonna limit the duty cycle of the pulse width modulated signal that we're sending to the robot to monitor the speed of the robot. For the gripper type, when we first initially started designing what kind of gripper we wanted to use for this project, we were looking at 2-finger grippers and 3-finger grippers, where the 3-finger gripper will actually overlap with the 2 fingers that are on top. This would provide like more carrying weight. However, there was a safety concern, like if there was some kind of unforeseen error within the system or a user error, and Doug, for example, would actually open the gripper, pots of water could like come down and spill all over the place or potentially hurt him. So what we decided to do was add hooks for the heavier load applications. This way, if something goes wrong with the system, it would have to be something catastrophic where the robotic arm would fall off the wall for it to hurt him. Otherwise, if there's like some kind of error, all the pot of water would just hang there, and someone could come and assist Doug in taking that down and like keeping him safe from that. One of the major concerns about the designs that we were having was the amount of torque that the weight of the motors and the load would put on the actual overall system. This would put pressure on like each of the joints. Could potentially, if heavy enough on the load, could cause a breakdown of the robotic arm. So as the design concept 3 with the sliding arm that goes like this right here, and then has an XY track, that is concept 3 on Kake slides. That would be the best option for us because 3 of the 5 motors are actually mounted near the wall, whereas the 2 other motors are actually just the motors to run the gripper, so that actually is not gonna be that heavy. Like the servo for the gripper to open and close the gripper is actually less than like a quarter of a pound. So, okay, for testing, one of the problems that we have in this on our project is that the mechanical portions of our project, the components are very expensive, and we aren't able to build a prototype. So what we have to do is test each of the tracks individually until we construct it at the end and test the whole system. But we can't build a prototype and make sure it works and scale up. Okay, so the proposed design solution, we decided to go with figure 3, which is the again, the rotating arm, since there's 3 to 5 motors on the wall, and that will minimize the amount of torque that's applied to the overall system. Again, considering like the gripper, we decided just to use a 2-finger gripper for picking up like small, lighter load applications, and using the hooks for heavier load applications, so that we avoid any failure.
My name's Tom Manner. I'm going to talk to you more about what we decided to do for our controller. So when we first started this, we had two different platforms came out at us that seemed like they were really obvious choices for control. So one is the Lego Mindstorms, and the other is an Arduino board. Both of them have been used for robotics, and there's a big base of things that have already been done. They're both programmable fairly easily. They're both compatible with all sorts of inputs and outputs, and they're both expandable. So we did some research on the 2 of these, settled on Arduino boards because they're much cheaper and they're easier to manipulate. We have direct access to all the pins and know what they all do and everything. And the board that's pictured here is called the Arduino Fio. On the back of it, it has a socket for an XB wireless, which is an RF radio, which I'll talk more about in a minute. Our controls for this, as we mentioned, we've got 5 degrees of freedom. The robot can move side to side, up, down, in and out, and then the gripper can rotate, open and close, which means we need at least 3 joysticks if we want to do this all analog. So we found 3 joysticks, all of which have a voltage input pin, a ground pin, and then signal pins for the X and the Y motion. And they're connected to these pins here labeled A, which are analog input pins on the Arduino that have a 10-bit analog to digital converter built into them. And those will measure a voltage between ground and the operating voltage of the board, and the board has 2 power and ground pins, 1 on each side. So we can take the joysticks and connect them directly to the board, and the board will do all of the work for us there. So that ended up being really easy to put together and get working. And then as far as like this gets us our signal, tells us where the joysticks are, and then as far as outputting that signaling and making the joysticks, or making the motors go, as was mentioned a minute ago, we're using pulse width modulation, which means basically we've got our square wave, and we're changing the duty cycle of that square wave. We're changing the amount of it that's a 1 versus a 0, and that these pins down here, there are a bunch of digital output pins here, and all the ones with a star, there are 6 of them on this particular board. They support pulse width modulation in the code. It's 1 line of code to take. You give it the duty cycle percent that you want as a number between 0 and 255, and it sets up a pulse width modulated square wave output there. So using the Arduino boards made a lot of sense for interpreting our joystick input and turning that into an output that we knew we could use. So then our next step was deciding how we wanted to get that signal from Doug's hands or whoever's using it to the actual track and all the motors and everything that'll be on the wall. And we decided we had 2 options. Obviously, we can wire it, just leave it and be physically connected. It would be very simple to do, having an input and simply routing that to an output. It would be cheap, but it's risky in a kitchen. He's in a wheelchair, and there'd be a tether running from wherever he was up to the wall over, the sink or the stove or whatever he's using. So we decided to do some research and look at wireless, and it turns out these wireless radios, this is about 2.5 inches wide and almost 3 inches long. They're really small. These are about $23, I think. And the range on these RF modules is up to 300 feet if you have line of sight. So we compared that with other wireless technologies. We looked at Bluetooth, which has a range limited to, I think, around 30 feet. It doesn't go as far. It did better through walls, but that's potentially a bad thing in this case. That was another thing, was RF. If he goes around the corner and bumps the controller, he's not going to move the arm in the other room, unless he's like just really, unless he's really close around the corner. And this made it a lot simpler. And then this board, the particular Arduino board that we had, comes pre-configured to work with this and has is programmable over the wireless port. It replaces the regular serial I/O pins on the board. And so there was about a $15 adapter that you plug one of these into and is plugged into the computer. And then when we change the code or update anything, you click upload and it wirelessly uploads it onto the board. You never have to touch it, which is great for us, but is even better down the road if they need to tweak the code or if something breaks and they have to replace a part. They don't have to force around hooking it, connecting it to the computer, or doing any of that. They can just plug in this wireless programmer and be set and done with it. And that's all I've got for you on the controller that we're using, the interface that we're doing. This is our fast diagram. Real quick, it's got some keywords, things, like sort of a general layout, I guess, of what our project's doing. And if you guys have any questions, feel free to ask them.
Any questions from the class?
Yeah.
What processor does that development board use?
It's
Amiga.
It's I think an 18 mega.
128.
128. Yeah, it's a 1. I don't remember if it's the 128 or the 320 that's in the file. But those are the two. I think those are the two that they use in the Arduino board. It runs at 8 megahertz, and the power consumption with the wireless radio in was the controller board was running at about 1.5 milliwatts. The receiver board was running about 2.5 milliwatts. Yeah.
Any concern about stray RF affecting the control of the activity?
Each of the XP radios is programmed with a PAN ID, which is basically its network ID, and it won't accept any input that doesn't encode that same ID. And it's a 4-digit hex code, so not really something we're concerned about.
That was a good question. That was one of mine. So I got another question.
Yeah.
Excuse me. What's the voltage of your servo motors? 24 volt?
They're
12
12 to 24.
12 to 24. So power supply considerations. So you're gonna.
We're going to use a FET controlled power supply, and the Arduino is going to control the gate of the FETs for the power supply, so it's going to be switching the power
My concern is
supply.
more the amount of current you might need to drive all of these motors. You're going to just use an off-the-shelf power supply?
We're not 100% sure what to use to power. We're still talking to our sponsor about what he uses. He's done a couple of robotics things in the past, and so we're still talking to him about what.
Yeah, but you need to consider that because you have 4 or 5 motors, right?
Yeah.
Are you going to have the ability for these motors to be operating in parallel?
Up to 2 of them.
Up to 2. So you need to figure out what the current requirements would be if in the worst case, when both are under full load, and make sure your power supply is strong enough for that. That's something you didn't mention. All right. Good. So before you leave, thank you.